Okay, welcome to Climate Change Part 2. I'm going to wrap up the climate change lecture this week while I'm out at a conference. And remember, we're framing this talk sort of in terms of this guy showing up at your dinner party saying, you know, climate change may be happening, but we don't know if it's man-made. We don't know if it's from CO2 emissions, and there's no data to support that. Okay, so I do want to reiterate that climate change deniers tend to, have a conservative streak in them. I'm not really trying to make any statements here, and I'm not saying that these people are bad or invaluable. I'm not trying to be that way. I just want you to know that, in my experience, climate change deniers often tend to look like this, and that's literally coming from my own family experience. This might as well be half of my uncles out there. Okay, and I love these people, and I think that they're valuable. I think that they just tend to be under-informed regarding the data, right? So I want you to be able to have conversations with people like this using real data, okay? Now I'm gonna skip down to where we left off. We talked about greenhouse gas concentrations and them rising in the atmosphere, okay? Now I'm gonna go to this flow chart here. This flow chart is showing specifically carbon dioxide and net accumulation of carbon dioxide in our atmosphere, okay? So combustion of fossil fuels transfers carbon dioxide from one reservoir, which are underground deposits in this case, to another reservoir, which is the atmosphere. Now, reservoir is a term. The term reservoir is something that environmental scientists use to describe a place where something hangs out for a certain amount of time. Okay, so underground deposits is a reservoir, or were a reservoir, for carbon dioxide, and it hung out there for potentially millions of years. Whereas the atmosphere is now a reservoir for carbon dioxide emissions, and it can hang out there for a certain amount of time as well. Okay, so that's what I'm saying when I use the term reservoir, and that'll probably come up again. All right, so here is a picture showing carbon dioxide fluxes between reservoirs, and we've divided it up into natural fluxes and anthropogenic fluxes. And these are in green for natural processes and in gray for anthropogenic processes. Okay, so look at this arrow here. Between photosynthesis and cellular respiration, we get almost the same amount of carbon dioxide going into the Earth reservoir as we get being emitted into the atmospheric reservoir. These numbers, again, come with a unit. In this case, we're talking billion metric tons of CO2 per year, okay? This is basically a wash on the planet. If you are talking pre-human civilization, the photosynthetic and the respiration rate have a nice balance to those CO2 emissions or sequestrations, okay? Weathering and volcanoes are also natural processes, but they don't really contribute that much to this, at least not compared to everything else, okay? So looking at land here and looking at these gray arrows, this is where humans come in terms of pumping atmospheric CO2 into the atmosphere, pumping previously sequestered CO2 into the atmosphere through industry and combustion engines, okay? So industry pumps out 26 billion metric tons of carbon per year. That is coupled with an increased uptake by plants, but it's nowhere near enough to compensate this increase from industry, okay? So that's all happening on land. Another thing that we're doing on land that's hurting our environment is clear cutting forests, right? Forests have a massive capacity to take in carbon dioxide as a function of photosynthetic processes. And when we clear cut it, we reduce the planet's ability to deal with that pressure. That's why people talk about the Amazon jungle being the lungs of the world, which is, a debatable phrase from a scientific point, but it comes from a good place, because if we cut it all down, we're really reducing the ability of the planet to sequester carbon dioxide, okay? Let's look at the ocean. The ocean has a similar situation going on. The absorption and release of CO2 just due to natural processes is essentially balanced. But when we look at anthropogenic fluxes over here, you can see that there's a net increase going into the ocean, okay? This is what is causing, ocean acidification, right? This imbalance here directly related to the ocean is what's causing CO2 to increase. You're getting pH to drop, causing ocean acidification. Okay, looking at this full figure, the whole square here, what we're finding is that there's a net accumulation of around 15 billion metric tons of CO2 getting pumped into the atmosphere per year, okay? And this is what is causing increased atmospheric greenhouse gases and increased radiative forcing as a function of those greenhouse gases. Okay, so not great, but now you have real numbers, okay? Your dinner guest says, well, I don't know, what are the numbers? How, does it take into account X, Y, Z? Boom, here's your data set. You show them this. So now, in the modern era, we study climate change using direct observation. So temperature, we have thermometers. Wind speed, we have anemometers. Air pressure, we have barometers. CO2 concentrations, we go out with our test tube, capture some air, and take it back to the lab. We've been doing this since the 1950s, okay? So we have direct observational data from the 1950s, and it's pretty staggering, pretty stark, right? Straight incline, okay? So here's your stuff to know. Use that as a study slide. So you get to this point where you show your dinner guests these data on CO2 emissions, the fluxes in and out of reservoirs, the direct evidence of emissions increased since either the Industrial Revolution or since the 1950s with direct data. But they come at you with this question. Okay, so we have data showing increased emissions, but how do we know that these emissions result in the changes that we're seeing? We don't have any data set from before 1940. We weren't there. We're just guessing that this is having an effect. Well, I would counter that statement by saying that we know what the climate was like as far back as 1 million years, okay? It is not a guess. This is hard data, all right? So all of the figures we've looked at so far have only been dealing with the first few thousand years. This figure, if you notice, the x-axis goes back 800,000 years, okay? Nearly 1 million years. So we know what the atmosphere was like in terms of several metrics, including carbon dioxide, for the last 1 million or so years, okay? How do we know? We know via proxy indicators. Proxy indicators tell us about the paleoclimate, which is just a fancy word for the climate of the ancient past. And these are vital for providing baseline data sets against which we can compare modern atmospheric conditions or climate conditions, okay? These proxy indicators are types of indirect measurements, but they serve as substitutes because we don't have time machines yet, right? But they're why we can tell somebody, we do know what happened back then, even though we weren't there. One of the most famous proxy indicators, and one that we're going to learn about and watch a YouTube video about in just a second, is ice cores, okay? I'm going to skip that one because you're going to learn all about it in a really interesting video. But in addition to ice cores, we have sediment cores drilled below bodies of water. So if you take a drill and you pull out deep core sediments from below the ocean and below ancient lakes, you can find out a ton of information because that sediment builds up in layers, okay? You can look at tree rings. That's a more recent indicator, but there are still trees that are thousands of years old, and there are fossils of trees that go back millions of years. And those tree rings and the sizes of those tree rings indicate information to us about the atmosphere. Pack rat middens are also really interesting, and they can fossilize, and they tell us about the different types of plants and materials that were in the atmosphere. And then isotope concentrations in coral reefs. So we're going to learn about isotopes in just a minute. An isotope is just a flavor of an element. So carbon has a typical weight of 12. Sometimes there's carbon 13, and those are called isotopes, those different weights. They're both carbon, but one's slightly heavier. Okay, so that's all I mean with isotopes. And with corals, they'll build up, huge mounds. Think about the Great Barrier Reef. These are the sizes of small countries. These mounds of ancient material that has been pulled out of the ocean. And the isotopic ratios, as you drill down into the center of those coral mounds, can tell you a ton about the atmosphere, okay? So I just talked a lot about them, but the main point there is that there are many proxy indicators, including ice cores, which we're going to learn more about now. So I'm going to start this video, turn my camera off.
You can see the little tiny air bubbles in there. Those are what we study. Basically, this is a piece of ice about 20,000 years old from Antarctica, and the bubbles trap air from 20,000 years ago. So we find out, what the air was like back then. Figure out if carbon dioxide had gone up or down, and what we've learned from that is that carbon dioxide is higher now than it's been for at least the last million years, probably the last 20 million years, but that's less certain. So it's really quite a dramatic thing that we humans have done to the carbon dioxide.
Hey, smart people, Joe here. So Earth's atmosphere and climate have changed in a big way, and they're continuing to change. There is no doubt about that, and we've known about it for decades. But Earth's climate has always changed throughout its history. So how do we know that this time is different? But we know because at places like the Scripps Institution of Oceanography in Southern California, we have freezers full of ancient ice that let us look into the past thousands, even millions of years, and measure exactly what Earth's atmosphere and its climate were like throughout deep history. I recently stopped by to visit Dr. Jeffrey Severinghouse, who studies ice cores. He's part of a team that's working to find the oldest ice on Earth. Because each of these little blocks of frozen water can tell us something about our planet's past, long before we existed, and where it's heading now that we do.
And inside these tiny bubbles in this ice are old bubbles of air that existed on this planet as old as that ice is. That was the atmosphere from the planet trapped in those little bubbles.
What happens in the polar regions is too cold to melt. So when the snow falls, it doesn't melt. It just piles up and piles up and piles up, and eventually turns into ice just from under its own weight. You think about what snow is like. So you got a snowflake, but you've got air in between the snowflakes, right? And so as that snow becomes more and more dense, it tends to squeeze out the air in between the snowflakes, but it turns out it doesn't squeeze out all the air.
As more layers of snow fall and condense, those tiny voids are literally frozen in time, layer upon layer. And there are a lot of layers.
Some ice cores have annual layers, just like trees do. How you can count tree rings to figure out how old it is. So some graduate student sits there and counts 50,000 annual layers.
Of course, it has to be a graduate student.
What a lot of work.
But to study ancient ice, first you have to find ancient ice.
Where are you doing this research? Where are you collecting these ice cores?
So this is from a place called Taylor Glacier in Antarctica.
Taylor Glacier is a 54-kilometer stretch of ice and rock. People like Dr. Severinghouse can read it like a book, full of stories about our ancient climate. Taylor Glacier is a special place because it's one of the few spots on Earth where the ancient ice has risen to the surface.
So you only have to drill down, maybe 5-10 meters to get the ice. Much easier than drilling a deep ice core, which is 3,000 meters and costs $50 million.
It's basically a cylinder that has tiny little teeth on the bottom. And when you rotate the barrel, it carves out the ice on the edges and leaves behind an ice core in the middle. And once the core is pulled up, it's packed up and sent off, carrying a slice of history inside of it.
It's a slow process. It takes like a month for the ship to get here.
Whether you're standing in the middle of the Amazon rainforest or at the North Pole, you're breathing roughly the same air. Our atmosphere is pretty much the same everywhere, which means that a tiny air bubble from that one spot is enough to paint a picture of what the entire planet's atmosphere looked like.
This is the freezer, and we won't be in there long, so don't worry about the cold. So this is what a typical ice core sample actually looks like. Notice that there's no bubbles. That's because when you get below about 600-700 meters, the pressure is so high that the air turns into something called a clathrate, which is an ice-like substance.
Clathrates are crystals where instead of bubbles, the molecules are trapped in a cage made by the bonds between frozen water molecules.
There's still gas in there.
Still gas molecules, but they're not in a gas phase.
Man, the patterns are so cool. You must just see randomly such cool ice phenomena.
Oh yeah.
It's cold in here. This cold.
Funny how that works, yeah.
Okay, but how do you get the ancient air out of the ice to measure it? I mean, without contaminating it with all this air around us.
So this is how we actually extract the ancient air, if you will. Take a piece of ice and put it in a vacuum flask like this and pump out all of the air the modern air that the air we're breathing right now using a vacuum line. This is a vacuum pump here. So we make a seal, and we pump out all the modern air, then we close this valve, and then you only have an ice cube and a little bit of water vapor, but no air. Then you melt the ice, and then the melting of the ice releases those little air bubbles.
So because you got rid of the now air, the only gases that are coming out are the ones that were trapped inside the ice.
Right. So then once we've done that, we can purify the gas a little bit by freezing the water.
So they pump out all the modern air, melt the ice to let the ancient atmosphere vaporize, refreeze the water, and pump that ancient atmosphere out so it can be measured.
This is a liquid helium tank, so it's cold enough that it's at 4 Kelvin. Wow, 4 degrees above absolute zero. It's cold enough that all the air actually condenses and turns into ice, air ice.
Every gas will
Every gas except helium.
Wow.
Yeah. Then we take it over here, and this is the analysis part of it. So this tube is actually a bottle. It's a very long, skinny bottle that's capable of dipping itself into the liquid helium.
You wouldn't want to be getting your own hands too close to 4 Kelvin.
No.
Now, the frozen air gets put into this, a mass spectrometer, which is a machine that we use to measure the masses of really tiny things. We measure the chemical composition of the atmosphere using isotopes. They're like different flavors of atomic elements. The isotopes, those flavors of elements, have unique masses, and the mixture of them in the air bubbles can tell us all kinds of things about ancient Earth.
We use the isotopes of nitrogen to tell ancient temperature, basically at the time that the snow was falling. Ordinary nitrogen has a mass of 14, and the rare isotope nitrogen-15 has a mass of 15. So it turns out the relative proportions of N15 and N14 are sensitive to temperature.
So whatever the temperature is at a particular time, it's creating different mixes of different flavors of
right.
gases in the atmosphere, like a fingerprint for the temperature.
Exactly, yeah, and that's trapped in air bubbles for posterity. So the sample here starts out waiting its turn. When its turn comes, this valve opens, and then the sample goes through this little tiny tube, and it leads very slowly into the actual mass spectrometer, which is here. Then it gets accelerated by 3,000 volt electrical gradient, makes the ions go really fast, and then they hit this magnet, and they're forced to make a 90-degree right turn. And in doing so, heavy things like N15 try to go straight, and lighter things like N14 get bent more.
It's like being in a car.
Exactly.
I mean, it's like, so you can't turn as fast in a big, heavy car.
Right.
So they swing out, and then the detector is seeing what's swung out farther.
Yeah.
So you're getting resolution of things that differ by a single neutron when they're flying through that curve.
Yep.
That's pretty cool.
The same idea can be used to find out more than just temperature. Labs all over the world use elements trapped in air, trapped in ice cores, to paint a map from our distant past to today. Oxygen isotopes can tell us how oceans changed. Mineral dust tells us about how the atmosphere moved around. There are chemical clues about early volcanoes, but maybe most importantly, we can trace changing levels of carbon dioxide. So the climate has changed before. How do we know that this time it's us?
So the way we know is that, just like we talked about for nitrogen, it turns out that carbon in carbon dioxide also has 2 flavors. Carbon-12, which is ordinary carbon, and then a very rare form of carbon, carbon-13. That's how we know that it's human caused. The atmosphere, as it goes up in concentration, CO2 concentration, the carbon-13 is taking a nosedive. And that's not what would happen if it was natural CO2, because fossil fuel CO2 is very depleted in carbon-13.
This comes from the fact that plants prefer to eat CO2 made of carbon-12. And when we burn fossil fuels made from those ancient plants, the fraction of carbon-12 in the atmosphere goes up while carbon-13 goes down. We've only been measuring carbon dioxide in the atmosphere since 1957, but using the data from ice cores, we can trace levels back way, way farther. And this is what we see.
CO2 was pretty flat for most of the past 1,000 years, all around 280 parts per million. Now we're going to add in the carbon-13 abundance record. That's this gold line here. You can see that that was also pretty constant for most of the last 1,000 years. But then around 1850, right when the carbon dioxide concentration started to rise, the carbon-13 abundance started taking a nosedive. So this really unambiguously tells you that humans did it. That's why I call it the smoking gun of human causation. There's lots of other ways we know, but this is the simplest to explain.
We are moving into uncharted territory. I mean, the last time something like this shows up in the ice record is around 55 million years ago, when a volcano popped up under an oil field and cooked basically everything.
It sent all of the carbon dioxide into the atmosphere. So the carbon dioxide in the atmosphere shot up. We think it basically quadrupled. And the climate warmed by 6 degrees. Most important thing is just right away to solve this global warming problem. We don't have much time left. We got to put aside all of our political differences. The health and well-being of the planet is so much more important than anything else. And we can do this. I know we can.
We can, but will we?
Okay, so that's the end of that video. Going back to the PowerPoint slide. I think that video is fascinating. Watched it many times, and I always think it's fascinating. I'm going to recap what they told you and what I really want you to know. I want you to know about this proxy indicator and the process. So they drill the cores, they ship it to a lab, they put the ice sample into a vacuum cube, they extract the air that's naturally in the environment that we're breathing, because that would be a contaminating variable. Once they've got the air we're breathing out of that vacuum tube, then they can analyze the air that was trapped in the ice. And they do this using machines called mass spectrometers. Those are literally things that can weigh molecules. Maybe you caught it, maybe you didn't, but mass spec, for short, mass spec machines can literally weigh the difference between one carbon-13 and one carbon-12 molecule. That's a subatomic particle difference, right? And so they're extremely sensitive, super, super cool machines. Now, what do they tell us? Nitrogen isotopes tell us about ancient temperatures. Oxygen isotopes tell us about how the oceans looked. Mineral dust tell us how the atmosphere moved around. Sulfates, so sulfuric compounds, suggest volcanic activity. And carbon dioxide, the most important one that we're talking about here, tells us how much greenhouse gases there were, or at least how much this particular greenhouse gas there was. So this is what that video told you. They also told you about the smoking gun. And this is really one of the best pieces of information to bring to this dinner party with your guest who's a climate change denier, okay? So they went over it kind of fast, and I'm gonna go over the details again with you here, and I'm gonna add a couple little things, and hopefully if you were confused at all, I want to rehash this just one more time. Carbon-13, different than carbon-12, rare, okay? Carbon-13 is rare, and it also decays, okay? Carbon-13 is not very stable, and it wants to go away. It'll naturally decay, okay? All of the carbon-13 in a particular sample, if you isolate it and you come back and measure it, by 60,000 years or so, it will be gone, okay? So it decays at a certain rate. And we know that fossil fuels are millions of years old. So most of the carbon-13 in fossil fuels has decayed if it ever was there in the first place. Fossil fuels are really depleted in this carbon-13 because fossil fuels are primarily made of plants. Plants prefer carbon-12. And so not only does it start as carbon-13 depleted, but you give it enough time and enough pressure, it turns into fossil fuel, and it's essentially got 0 carbon-13 in it, okay? Now, we take that fossil fuel out and we burn it, and that's what we're seeing here is just an increase in total carbon-12, okay? So carbon-12 is dramatically increasing because we are burning it in our fossil fuels, and the fraction, AKA the percentage, the number of carbon-13 molecules per unit air, if you go out and you trap a cup of air, the number of carbon-13 relative to carbon-12 has been plummeting, okay? So that's a fraction, and that's one thing that I think the video didn't really go too deeply into or deep enough into. That's why these things are crossing, right? That's why we're seeing it go like that, is because this is a ratio, all right? And that ratio's all screwed up from a natural process because we are taking carbon that was sequestered and blasting it into the atmosphere, and it's all carbon-12 that we're putting into the atmosphere. So that's the smoking gun, okay? That's your evidence. You present that, you show your friend at the dinner party the video, you talk about the fraction, you explain what isotopes are and how we measure them. And this is what they say. Well, they say correlation is not causation, okay? That's a statement you've probably heard before. And what that means is that two things can be correlated, but not causal, don't have a causal relationship. So look at this figure here. Per capita consumption of cheese versus the number of people who died by becoming entangled in their bed sheets. Okay, these figures look almost exactly the same, and it would suggest that as people eat more cheese, they're also at higher risk of becoming entangled in their bed sheets. That's ridiculous, right? There's no correlation, or there's no causative effect there. There's only correlation, okay? Another example is cigarette smoking, and this is one that has stuck with me. Maybe it'll stick with you. Cigarette smokers tend to have lighters also, and cigarette smokers tend to have a higher incident of lung cancer, okay? So how do we know that it's actually the cigarette smoke that's causing the lung cancer and it's not having a lighter in your pocket? They're both correlated, right? People that have a lighter in their pocket have a higher chance of getting lung cancer. Same with people that are smokers. Which one's the causative agent? Of course, we know it's actually the cigarettes, but lighter in pocket rate is also correlated, okay? It's not causative, but it's correlated. And so this is the argument that people tend to make. They say, well, okay, CO2 is rising, and I understand the greenhouse gas process, but we don't know that the CO2 that we're putting into the atmosphere is actually creating this change. Okay, we're putting more in, we can see that, but why is that creating change? We don't actually have that data. I'm telling you that they were right as of before 2021, okay? There was so many lines of correlative data that you can infer causation before 2021. So this isn't new, but this is really the nail in the coffin, okay? And so this paper here made headlines in the scientific world because for the first time, it gave direct evidence of increasing global radiative forcing, and it could separate out human CO2 emissions from natural radiative forcing emissions. So in other words, it said how much natural radiative forcing is happening versus how much is directly related to our CO2 output. And we have instruments now that are sensitive enough that they can parse those two out. Before 2021, our instrumentation wasn't sensitive enough, okay? So the correlation and causation argument is also now dead. We have a causative relationship here. Okay, so with that, here are your things to know. What are proxy indicators? What are isotopes? Why are they important? How are cores studied? What is the smoking gun of human causation? And talk about directly measuring radiative forcing increases. And all of the questions that your family member, your loved one that is undereducated about climate change factors, all of their arguments that we've presented here are directly answerable using hard science and real data by you now. So with that, I will conclude the climate change lecture, and I will see you guys next week.